So if you look at the tan theta here and here, they have line L1 and L2 have the same. Because the line L2 passes through origin, observe that its equation is y is equal to mx. There is no constant because the point 0, 0 lies in L2, where the equation of L1, it must look like what? It must look like y equal to mx plus c. There would be some constant because the line does not passes through the origin. C is not equal to 0. Okay, how to find out C? Take any point on this line, any point, what you wish, any point, maybe say u comma v, or rather, yeah. So if you take any point here, so what would you get is that v is equal to mu plus c. So c is equal to v minus mu. Okay. This is one form, y equal to mx plus c form. In fact, the slope can be, if you have a 2 point on the line, then everything could be understood. Okay, now let's take that kind of thing, is that to know m, to note that c, given 2 points on the straight line. So let's draw a straight line in R. I have a point over here and its coordinates are u2. I have another point over here, its coordinates are here. And suppose I have a point over here, which is the point y comma x. Okay. Let's draw perpendicular from these points to x-axis and y-axis. This point is over u1 comma u2. So this is axis. Okay, and this is the case. Observe that this angle is theta, right? So similarly, so this drop perpendicular, this length is u2, this length is x, and this whole length is v2. And similarly, this length is, this is u1, while this length is y, while this whole length is v2. Okay. Now, because these are perpendiculars on x-axis, this is 90, this is 90, this is 90. Let's call this point as A, B, C, D, and suppose E, F, G. Okay. What do we have? We have that triangle ABC triangle, not ABC, rather ABG, ACF, triangle ADE. They are similar triangles. Okay, this angle is same thing as this angle, is same thing as this angle. These lines are parallel lines. So let's call this thing as maybe say, so yeah, L1 dash, L2 dash, L3 dash, L1 dash parallel to L2 dash, parallel to L3 dash. Okay, so we get that these three lines are parallel. So we can use corresponding angles again. Angles again to get the following thing. Angle AGB is congruent to angle AFC is congruent to angle AED. These three angles are congruent. So this is what we are shown. Okay. Now just rub the below part so that more space is there. So I have the line. This is our line. Maybe so let's call this line L. We are trying to find the equation of this line. We have 2 points on it, U1, U2, and V1, V2. Okay. Over here, so I have what here? Y-axis. So observe that. Similarly, let's rub this lines also. This is also not required. So tan of theta is equal to the opposite side upon the adjacent side. So for the triangle ABC, this works out to be upon U2, which is the same thing as x upon opposite side, so y upon x. This is y, this is x, so y upon x, and similarly, which is the same thing as V2 upon V1. Okay, so this length upon this length, this length upon this length, this length. Observe that the other thing could also be done. If you draw from this point, draw this kind of a line, which is okay. If you have this thing, now this length is V2 minus U2, while this length is V1 U1, and this line is parallel. This line is parallel to this line. So again, this angle becomes theta, just like this angle. So what do we have is that this is the same thing as V2 minus U2 upon V1 minus U1. And if you observe that this triangle, similarly if you look at this triangle, then this is the same thing as y minus U2 upon x minus U1. if you draw a parallel line to this thing, to x-axis, this one, this is the same thing as v2 minus y upon x minus v1. Okay. So these are all things as tan theta, so this is called as the slope. Okay, and theta is not assumed to be either pi by 2 or minus pi by 2. In this case, the equation is nothing but simply y is equal to, not y is equal to 0. So what would happen is that the slope is infinity, so you get that x is equal to 0 in these two cases. So we'll assume that theta, not pi by 2 or not minus pi by 2. Okay. So I'll rub this part. So that how to get an equation. So given 2 points and x and y is any arbitrary point on that line, so the equation becomes the following. So m is equal to, this is tan theta, is equal to v2 minus v1 upon u2 minus u1, that is equal to y minus u2 upon x minus u1. So considering these two equations only, what do we get? We get that x minus u1 into y minus u2 into, here it is u1. So what we have left was, this is u1 times v2 minus v1. Okay. I'd rather what we'll do is a very simple thing. Since this is m, so let's call this thing quantity. Okay. So, so this is the point u1, u2. This is the point v1, v2. The difference of y coordinates are different. So y minus u2 upon x minus u1 is equal to m. So y minus u2 is equal to, so y minus u2 is what? If you call this m, this and this, m times x minus u1, that becomes what? Y is equal to mx minus mu1 plus u2. So this is the quantity what you are looking for. This quantity is called as small c. Okay, so we have what? So we have the equation becomes now of the form. This equation of the line L is mx plus c. Okay. So let me draw this one. Suppose there is a graph of some function. Consider this. Closed interval A comma B. So this is the line. It is the line joining the point P and Q. Okay, and you can see that the line joining P and Q is above. So this is the graph. graph of this thing. So this line is above the graph. Okay. If it is, so in this domain, such a function would be called as a convex function. Okay. There is a convexity over here. You can see this part. Just like you have a convex glass lens. Okay. So we'll try to formulate the condition. So what is, we have 2 points. So what would be the slope of this line segment at least? So the slope, so infinite line PQ, if you extend it here and if you extend it there, then the slope of the line is nothing but f of b minus f of a upon b minus a. This is the slope of the line. In fact, if you take any point here, maybe say x comma y, then this is also could be written as y minus f of a. Suppose this is the point, suppose x comma f of x. Then not f of x, it would be x comma y. It's not on the graph. Then this is y minus f of a upon x minus a. So this is from this thing you can find the equation of the line of the PQ. Okay. So we'll try to focus on a line segment and try to see that convexity, the condition of convexity and differentiability, relation of the second derivative and convexity. Let's draw a line first. Okay. We have this thing. This is the line segment. We'll try to see a condition from convexity that you take a closed interval 0, 1. Okay. Take a closed interval 0, 1. You want to map this closed interval 0, 1 to the part on this line. Okay, let's take a point over here. This is this one. And suppose let's take another point over here on this line. This point is u1 comma u2, and this is x comma y, u1 comma u2. Okay, this is this line. This is 90 degree. This is 90 degree. This is 90 degree. Okay. What we are interested in is that in this segment we want to map. We want to map this 0, 1 interval. Okay. We'll call this thing as a t belonging to this interval. So 0 less than equal to t less than equal to 1. How shall we do that? On this only particular segment at t of 0, what we want is that t equal to 0, the point must give rise to u. Let's call this thing as point u, point as v. Okay, and let's call this point as p. Okay, and t equal to 1, you want it to be v. Okay, all the points and so on. Right. So what's the slope of this line? The slope of the line, this line, when we look at rather this one, in this direction, it is extending infinite on both sides. M is difference in y coordinates, which is this minus this, v2 minus u2 upon v1 u1, and that is the same thing as which is considering with respect to this triangle. This is over the point, this is a point. So this triangle. Okay, if you consider this triangle, then we get that y minus u2 upon x minus u1. Right. Okay. what could be done is that interchanging of these two parts. And why we can do is that observe the following fact, that here is u1, here is x, here is v1, here is u2, here is y, and somewhere here is v2. So u1 less than equal to x, strictly less than equal to v1. Okay, we'll take the point x to be this one. We can have strictly less also, and similarly u2 strictly less than equal to y, strictly less than v2. Okay, let's take another two. So observe that x minus u1 is greater than equal to 0, and v1 minus u1 strictly greater than 0. Similarly, y minus u2 greater than equal to 0, but what do we have? v2 minus y strictly greater than 0. This term over here. And what was m? M was this thing after, so m was v2 minus u2 upon v1 minus u1. That is the same thing as y minus u2 upon x minus u1. So u1, right? So what do we have? Cross multiplication. So x minus u1 upon this is v1 minus u1. v1 minus u1. This is the same thing as y minus u2 upon v2 minus u2. Okay. Now you look at these quantities which are mentioned over here. If you have here v1 minus u1, this is strictly greater than 0. But x1, this is non-negative. To call this object as t. Okay. So t is this also and t is this also. So if you assume t is equal to x minus v1 minus u1, you clearly see that t is greater than equal to 0. And this term is non-negative, this term is positive, so this is there. And observe that from the figure, what is this length? This figure, what we had over here. So this length is x minus u1, this length, x minus u1, and this length is v1 minus u1. Okay, so this length is larger than this length. In other words, this is in the denominator. So the value of this thing is t strictly less than 1. Okay, so x minus u1 and so on is strictly less than 1 because of this fraction. So 0 less than equal to t strictly less than 1. And the case is considering that because we are considering the point x comma y is not equal to u1 v1, but at t equal to 1, what happens? So if, okay, so this is, with this t we have this one, at t equal to 1, this becomes what? X minus u1 upon v1 minus u1 is equal to 1, thereby implying x minus u1 must be the same thing as v1 minus u1, thereby implying x is equal to v1. So the point is that in this diagram, so point this one, x coordinate, if you take this one, then it gives you the value t equal to 1. Okay. The same thing, if you put t equal to 0, this and this, at t is equal to 0, this is non-negative term. This is strictly positive here. If you see v2 minus u2, what is v2 minus u2? Is it written? v2 minus okay, so y minus u2 is written and v2 minus y. One more could be written here also from the diagram itself. You can clearly see I have this length, so v2 minus u2 is strictly greater than 0 if the points are distinct. Correct? So similarly, if you take this as 0, so you can write here this is strictly greater than 0, v strictly greater than 0. This is t. Assuming this is this value, so t is lying between this thing. Same can be argued here at t equal to 0. From this equation, y becomes u2 and x becomes u1. Okay, and similarly t equal to 1. So you can write here just this part. What does this imply? At t equal to 0, this is the point u1 comma u2. At t equal to 1, this is the point v1 comma v2. Okay. So from the closed interval, so the closed interval 0, 1 can be mapped. So at 0 is here, at this is 1. Okay. Now let's observe that if x comma y is the place, the point P is there. So point P is there, this is there. Because t is defined this way, we look at this one, what do we get? Again rubbing this part. Using these two equations, if you look at this one, so t times v1 minus u1 is the same thing as x minus u1. Okay, so what do we get? Shifting on this on the right hand side, so tv1 minus tu1 plus u1 is equal to x, which is what? In this thing common u1, so tv1 plus 1 minus t times u1 is equal to x. The same thing is giving me this point. So given a t, you can go to the x. Given a x, you can find the value at where it is the t. Okay. And similarly, here what would I get? Considering these two equations, I would get that tv2 plus 1 minus t u2 sorry, is equal to y. Okay. So at one particular instance t, if you take the t belonging to 0, 1, it would go to the point x comma y, which is the point P. This is this one. So t equal to 0, this is t equal to 1, and t belonging to, say, at one particular point. So we get this thing. Okay. So what would be phi of x? So phi, if some function is there, phi, some function is there, phi, because x is t v1 plus 1 minus t u1. Phi of x is nothing but phi of tv1 plus 1 minus t u1. Okay, this would be phi of x. And suppose y is belonging to what, not the graph, or y belongs to, let's write in more proper sense, x comma y. graph of a function, maybe say f, rather 5 is, then y is equal to phi of x. But what is y? Y is tv2 plus 1 minus t v1. That must be something as phi of tv1 plus 1 minus t v1. Okay, just check what it would be. Not v1, sorry. So you have this thing, right? This could be rearranged in the following manner. If you want 1 minus t u2 plus tv2, this is equal to phi of 1 minus t u1 plus tv1. You have this one. Okay. So this is our x, small x, this is small y in the diagram. This is the value of phi of x, and this is the y corresponding x comma y. Okay. If y is in, the condition is that if y belongs to the graph of phi. If y does not belong to the graph of phi, then that would be the something else. So this value would be tu2 plus tv2 would be the y coordinate and so on. Okay. Now let's come to what is the convexity, what we were discussing. You have some graph, maybe say in this way. This point over here is a comma 0, b comma 0. This is the line joining this thing. So we have seen the slope also and so on. If our this point P is there and Q is there, so rather what we would say is that P is maybe say U1 comma U2 and Q is V1 comma V2. So what we have is that A is nothing but U1 and B is nothing but V1. Okay, so this is the graph. So suppose f is the function here. This is the graph of f, this one, and this is the line segment joining P and Q. Okay, there is a convexity in this part. Okay, it's lying above. Okay, so let's try to formulate the condition of this convexity. So V2 is equal to so what's the equation of the line? The equation of the line is if you take a point over here, maybe say x comma y, then okay. because y minus u2 upon x minus u1, this is the same thing, right? v2 minus u2 upon v1 minus u1. So what do we get is that u2 is u2 and v2. We try to multiply this one. So y minus u2 multiplied by v1 minus u1. This quantity is the same thing as x minus u1 multiplied by v2 minus u2. Okay. So opening one. So y into, and rather what we would do is that I want just y. So y into this is the same thing as x into v2 minus u2 minus u1 into v2 minus u2. So if you look at this object on the right hand side, this and this could be written as u2 times x minus u1. Okay, and what happens here with respect to v2, this term and this term, this becomes plus v2, so x minus u1. Okay, and then this is your this part is still remaining. So for this part, what do we do is that we send this u2 on the right hand side. If we send this u2 on the right hand side, that becomes with what sign? Plus sign. So that is what? This is u2. This is u2 with what sign? Minus is plus. This is plus and here it is a minus sign. You have to check. This is minus, this is the sign of u1 has to be plus, and then u2 and so on. Okay. From this, what do we have is that u2 is v1 minus u1, right? And this is this one. So sending this on the right hand side, what does this imply? This implies that y into v1 minus u1, this is equal to, now u2, this sign becomes plus. So this bracket with this bracket, this is plus u1, this is minus u1. That cancels. So that is v1 minus x plus, what is it? This is plus v2 x minus u1. This one. So this could be written as so this could be written as what? Plus u1, right? So This also could be written as u2 now. Since the sign of this thing, yeah, okay, fine, is positive, this is your y. So y becomes what? Or alternatively, u2 was f of b times f of, so this is just v1 was b, u2, what is u1, u2? u1 is a, u2 is f of a, v1 is b, v2 is f of b. So what do we have? This is the alternative thing. So you can write y, which is what? So this was the point. So if you look at here, this is the secant, and we are asking for the convexity of this function in this domain. So the graph is lying below. We'll formulate the condition for below. But what we have done is that for this line, we have seen that how to write this line as a combination of this coordinate, this coordinate, this coordinate, and this coordinate from y equal to mx plus c, or the 2-point form. So what do we have is that, let's consider, since strictly bigger than u1, strictly bigger than u2, what does this imply? v1 minus u1 strictly greater than 0. So 1 is equal to v1 minus u1 upon v1 minus u1, that is equal to v1 minus x plus x minus v1 upon v1 minus u1. So if you separate it, 1 is equal to v1 minus x upon v1 minus u1 plus x minus, here it is u1, sir. u1, this part and this part, which is nothing but this part, which is this part, this is this. Okay. In other words, if you call, and as we have observed that this object is between 1 and t, this object is 1 and t. When this becomes 1, if this becomes 1, this becomes 0. So x is u1. When x is u1, y is v1, and so on. So you can, it is nothing but t plus is the form of t plus 1 minus t, which is equal to 1, t belonging to closed interval 0, 1. Okay. Here it should be v2, sorry. This is v2 here. Okay, so this is the value of y. Okay, The moment you have the value of y, we have also seen that 1 is equal to v1 minus x upon v1 minus u1 plus x minus u1 upon v1 minus u1. So multiplying f of x, what do we have? We have that v1 minus x upon v1 minus u1 times f of x plus x minus u1. Okay, this x minus u1 divided by v1 minus u1 times f of x. Okay, I have this term. Okay, f of x is a real valued function. This is a real number. So y minus f of x, the term works out to be what? So if you look at this and this, the first term, this term and this term, which is v1 minus x upon v1 minus u1, f of a minus f of x. Okay, and the term plus this term and this term is same, x minus u1 on v1 minus u1 multiplied by this minus this, which is f of b minus f of x. Okay. So if you look at this picture, here is a, here is x, here is b, f of x, f of a, which is u2, y is f of x, and then v2 is f of v1, which is f of b. Look at this thing, so we'll change the sign of this thing. We'll take rather f of x minus f of a. So this becomes what? If you write here, there is a minus sign here, we can bring here, and then this bracket becomes f of x minus f of a. Okay, this is y minus f of x. Assume that the following condition. So we will use a mean value theorem, namely LMVT. So the condition must be satisfied. So we require f, the function, to be continuous on the closed interval AB, and we also say that it is twice differentiable. It's a twice differentiable on the open interval AB, such that the second derivative is always non-negative for all s belonging to the open interval AB. Right? This is the case. This is the Lagrange mean value theorem. So we'll assume this condition on f, and we'll try to look what happens. Okay. So we have this below thing, which is this condition. If you look at here, so we break into this interval a to x, and also similarly this interval. Okay. So what do we have? Once you break this interval a to x, so here is x, here is a, here is, sorry, the x is on the, a is on the left hand side. Here is a, here is x, here is b. This interval and this interval. So the Lagrange mean value theorem, what would happen? F of x minus f of a. So if you apply, there exists a C1. C1 here belonging to open interval, and C2 open interval here, such that f dash of C1 is equal to f of x minus f of a upon x minus a, and similarly f dash of C2, this is equal to f of b minus f of x minus f of x upon b minus x. Let's substitute this value. So what is f of x minus f of a? X minus a times f dash c1 here, and b minus x times this thing here. So c1 is an open interval, okay, a comma x, and this is an open interval x comma b. So we'll just rub this part, and in here itself we'll substitute y minus f of x is equal to minus of v1 minus x upon v1 minus u1 multiplied by x minus a into f dash of c1 plus, what do we have, x minus u1 divided by v1 minus u1 multiplied by b minus x times f dash of c2. Okay. So we have these things. Okay. If you look at this object, what is A? A is what? A is u1, B is v1. Okay, so this is this term over here. We can replace this v by b with v1, and similarly a with u1. So what does this become? So you have x minus u1 term, x minus u1, v1 minus x, v1 minus x, and so on. So the things are common here. So let's rub this part. Y minus f of x works out to be x minus u1 times v1 minus x upon v1 minus u1 multiplied by, now there is a negative term here, so this becomes f dash of c2 minus f dash of c1. Okay. So what do we have? The moment you have this thing, again, if you look at this object, so a is strictly less than c1, strictly less than x, is strictly less than c2, is strictly less than b, this term. You consider this interval now, c1 to c2, and look at the derivative. Again, for this derivative, we can apply LMVT. So because it is second differentiable, so this the first derivative is continuous on the closed interval c1 and c2, because it's a second differentiable throughout the open interval. So the point is that this is continuous, right? This is continuous and that is differentiable. So applying LMVT to f dash, okay, on the interval closed interval c1 comma c2, continuity of this thing because the second derivative, and differentiability of c1 comma. So so this difference, this is the endpoints of this interval. So there exists a c3, there exists a c3 belonging to open interval c1 comma c2, such that f the derivative of this function at c3, this is equal to this value, f dash of c2 minus f dash of c1 upon c2 minus c1. Okay, so this is the Lagrange mean value theorem applying here, in other words. So this difference is this term multiplied by this thing. So let's replace this one. So what do we get? One more term we get here, c2 minus c1 multiplied by f. Now this is the double derivative of c3. Now you observe the terms. Where is c2 minus c1? So c2 minus c1, this term is positive. v1 minus x, v1, this is your b is equal to, this is v1 and this is your u1. v1 minus u1 is positive. v1 minus x is also positive. v1, so this whole term is what? Greater than or equal to 0. Why these terms are greater than or equal to 0, and we are assuming the derivative is positive. If the derivative is positive, what does this imply? This implies that y minus fx is non-negative. If y minus fx is non-negative, that implies that y is always greater than or equal to f of x. But y is where? Y is on the secant line. And this is the convex. So what we have just shown? We have shown that for a function defined from an interval to the real, so it's a real value, and if the derivative is non-negative for each of the points in the interval, you take the closed interval, then such a function has to be a convex function. In other words, every point on this thing lies above this thing. The y coordinate is above. The y coordinate of this thing is here. The y coordinate is here. Y coordinate lies above, and so on. Okay. An example of this fact. What would be an example of this fact? And so let's see. F of x equal to e raised to x, as familiar with the natural function, rather exponent. You take any interval. F dash of x is e raised to x. F double dash of x is also e raised to x. That is the thing. And e raised to x is always greater than 0 for all x belonging to the set of real numbers. So what does this mean? This means that the exponent function on a real line or any subset of the real line is convex. So it bends below. So if you try to draw secant there, it always lies above. Okay, so we'll use this convexity of this explanation to prove what fact? Young's inequality.